All right, so I'm making the key here, so I just thought I would record it for those of you that are interested. So the first one is a cubic, right, function. So you graph it on your calculator, and so some reference points that definitely should be on there is your y-intercept. There's a max and a min in this case, right? You want that. And it says for the first, to graph it for the first 80 feet of the flight. So I do want the 80, right, 80, 19.18 on there, and then it keeps going. Um, Obviously, this would not be realistic after a certain distance because it would just keep going indefinitely into infinity. So you'd have to stop it at some point. But anyways, this is what we have. Distance and height, units, equation, proper scale on x and y. And so there we go. The lowest height it ever gets is 3.58, which you already found anyways. And after 25 feet of horizontal travel, you're at a height of 9.65 feet. So nice and straightforward here. The next one is asking us to examine the growth of a bean plant under different conditions. The data from one of the trials appears here. So in this case, the first column is your X and the second is your Y. So we know that we're talking days and height, right? In this case, we actually have the time in our X axis. So we'll determine that. I already went ahead and entered it. So we're going to perform the regression, linear, logarithmic regression, natural log, right? So we just go ahead and do what we always do. There we have it. So there's your equation, 6.445 plus 5.547 natural log of x. There's my equation. Perfect. And you also have, always remember to kind of predict what is this graph going to look like, right? So if b is bigger than 0, this is b right here, we know that it's going to be an increasing function like this. It's going to cross the x-axis. It never touches the y-axis, right? So there's our asymptote here. X is equal to 0. And so there will be an x-intercept in this case, which you want to include. You probably don't, we don't want negative values in this case because it's the height. So, I mean, it could represent the height underground, right, as you're planting the seed. So just read carefully and answer accordingly. This one will also have the point 1a is usually on here. That can be included depending on the context, of course. So we're not graphing, just coming up with the equation. So B would be determine the average height of the plants after 30 days. So we are given the time in days already. So we're going to figure out our y. So you can actually use plot 1 here. Sorry, I'm going to erase everything else. So you could do a zoom 9, right, trying to model this. If you look at your window, your x max is at 16. We need to go to 30, right? So that'd probably be a good idea to go to 50, go a little bit under, a little bit over, and there's your graph. It's much better. Second trace 1, x is equal to 30, and that's 25.31. We are, it doesn't say, let's see. Average height of the bean plant. It doesn't say the units. All right. Well, in that case, you can go units, right? If it's inches, centimeters, it doesn't matter. Okay, that's okay. C, oops. A logarithmic function can be used to model for this model with some limitations. Explain how one of either the domain or range is limited in this situation. Okay. I would say that when it comes to your range, right, because this graph actually keeps going up indefinitely. when it comes to your range, right, the plant will stop growing at after a certain time. Okay, this graph shows indefinite growth. Okay, so you can make a comment on that. When it comes to the domain, technically, right, days can just keep on going, but you could also say that it's not realistic to assume that time is indefinite, like, because at some point it will stop growing. I'm going to focus in on my x-intercept. Let's see. And that's 0.310. So I think that is acceptable, right? It takes a little bit of time until you start seeing the plant appear, right? So I would say the domain is okay on the low end, because on the range, remember, there's a low end and a high end, right? So the low end of 0 is fine, but this, which would be round, right? This is not fine, right? Not realistic. So we're saying, hey, there's a limitation here. The domain would technically be from 0.31 all the way to infinity. And it's not realistic to assume that the plant will keep growing indefinitely, right? In terms of time for indefinite amount of time, right? A plant can't grow for an indefinite amount of time. Okay. You could also say that technically, there's a time 0, right? But that would represent a negative height, right? So there's a restriction there, but I think you get the point. Usually, if you have one argument to make, it's good enough. Okay, page 59. The volume of a box design made from cutting and folding pattern as follows. So you have that pattern. So you have the box width, that'd be your L1 or your X, and the volume, which would be your L2 or the Y. So we know that every point, once we perform the regression, will be width and volume, and the volume resulting from that. What type of function do you think would best fit the relation between the width and the volume? Since volume is a cubic measure, okay, we should perform a cubic regression to model this relationship. Okay. You could also make a case that if you plot those in, that you see like a cubic, the scatter plot shows a cubic relation, right? It has the shape of a cubic. So we're going to go ahead and do this. Oh, that was actually the wrong way. Cubic regression is right there. There it is. Oh, we should look at the scatter plot, right? It doesn't, quadratic, it would look like it would have to come here this way, right? But you can definitely say that there is no symmetry there, and the scatter plot kind of does look like a cubic. We know that when volume is something that is being mentioned, that it's a cubic measure. It measures three-dimensional space. So there you have it. So determine the line of best fit. So we're going to go ahead and go stat calc cubic reg. Okay, and I already did that. I'm just going to go ahead and do it again. So it's y is equal to negative 0.002x cubed plus 0.06x squared, and C and D are 0. Okay, so watch out for scientific notation sometimes. All right, so C, what is the maximum possible volume of the design? Okay, what width gives this volume? So you should remember that let's adjust our window a little bit to include negatives. I'm going to go x max up to 50, y min I'm going to go -1, x max to 10, something like that. And this cubic actually, right, turn number 1, turn number 2, but we do expect it to go down, right? So it's coming this way and then down like that. But the max, we don't consider anything below because then the volume would be negative. So it kind of stops here. After this intercept, even if it would come back up, we no longer count this. The box can no longer be created past this point. And so we just find the max. That's 20. Right, so second, trace max, and we have 28, right? So maximum volume would be 8 liters, and then maximum width would be therefore 20 centimeters. Okay, so you got to make sure you use the appropriate units and also state which one is which. Don't just give me this. Okay, D. What width gives a volume of 5 liters? Show how you determined your answer. They're giving you volume, right? The y value. So we're going to go y2 is equal to 5. Then second, trace 5 for intersect. There it is. There are 2 widths that make that happen. It's kind of like the quadratics unit, right? So we can say that x1 would be 11.68 centimeters. x2, go here. That is 26.42 centimeters, right? Then we can just say a width of either 11.68 centimeters or 26.42 centimeters will result in a volume of 5 liters. Okay, there we go. E, what is the domain of this function based on this context? Explain your reasoning. So for volume, we would go for the domain and range. Range talks about the y value, so that would be a volume of 0 all the way to a volume of 8. And you might argue we should not include that as 0 because that would not be a box. But in this course, we just do it because it's possible. And the domain also starts at 0. Like if you look at your x values, it starts at 0. That's your actually y-intercept and x-intercept. And it goes all the way to this point right here. Okay, so we need to figure that out. That's 30, 0, 30, 0. So we're going to go y2 is equal to 0, second trace 5, x is equal to 30 centimeters, right? So, and if you think about it, that is the furthest right you can go, 30 centimeters. So the width between 0 and 30 centimeters would do. Okay. That is it. Next we have page 60. That's an exponential function, right? If this is greater than 1, we have an increasing function, right? So this is my asymptote. And so this will go like this. But we will most likely focus on the first quadrant, right? So we'll have a y-intercept, no x-intercepts. Where P is the population and T is the number of years since 1960. So time and population since 1960. So if this is 1, right, it would be 1961. If this is 10, it'd be 1970, right? So we just add that time to this to actually find the year. Create a graph of this function from 1960 to 2020. So we'll do that. So let's see what we know. Increasing, right? Exponential, check. Increasing, check. The initial population is 5,620. Check. And so we're supposed to go from 1960 to 2020. We'll adjust that in a bit. So I first need to find my ruler. Let's see here. Okay, here we go. Time, or in years, right? Since 1960. We're going to make sure we label that correctly, okay? And then we have here this population. So we're going to go from 1960, which is our 0, all the way to 2020. So that's, if you think about it, that's 60 years worth of data, right? So let's see how we can make this work. 10, 20, 30, 40, 50, 60. 10, 20, 30, 40, 50. That works. Every other marking I label. And population starts at 5,620, but it's going to go up, right? Because we know that it's increasing. So it's going to go up. So, and we want to include these years. So we're going to first figure out after 60, like at this point, we're going to figure out that point we want to include, and then we're going to adjust our Y scale. So second trace 1, x is equal to 60. We're going to figure out y. So let me just enter that first. Turn off plot 1. And there's no y-intercept, so no x-intercept, so no worries about that. The power of x. I'm going to adjust my window. I'm going to make sure I include at least 80 y min, y max. If it starts at 5,620, it's going to go up from there. So I don't know, I'm going to go 25,000 for now. It's pretty good. Maybe a little bit higher, 35,000. There we go. So second trace 1, x equals to 60. It doesn't show up on my graph, but can't see that. That's 36,554.61. Okay, so that's what I need to include So technically I should have gone 40,000 or something like that, right? Then it shows up on my graph. So that means I'll go all the way up to 40,000, okay? So let's see, 10,000, that doesn't work, so I'm gonna have to go smaller here. 10,000, 20,000, 30,000, 40,000, that's it. Okay, so you choose your scale, perfect. 60, I'm at 36,000. So right about there. So this would be my 10,000 here, 5,600 and something is here. Maybe find one more along the way. And x is equal to maybe 30. 14,300. 14,333.07. So that's going to be my reference. 14,000 is right about there. So I have enough now to show that. So P is equal to 5621.0317 T. All right, so that's my graph. So this, you kind of should know by now how the steps work. According to the equation, how many people will live in the municipality in 2015? So that's time, right? It's an indication that we can figure out time. So time would be 2015 minus 1960, right? And that's 55. So second, trace 1, x is equal to 55. So it would be 31,273. 0.392, which is approximately 31,273 people. Okay. C, by what percentage is the population growing? And that is coming from the bracket in here. If it's greater than 1, right, we just subtract 1 from this. 1.0317 minus 1 is 0.0317. Multiply that by 100, it's 3.70% per year. Okay. D, if the municipality continues to grow this way, when will it reach 50,000 people? That's D, right? So we need to make that our 50,000 and then find the intersection between the 50,000 line and the curve. And I probably won't fit that, right? Yeah, my window isn't. I will go 60,000 here. There we go. And that's 70.04. It does say when. So years. So we'll go 1960, sorry, plus 70.04 is going to be 2030.04, which is approximately in the year 2030. In the year 2030. Okay. There is this question. Let's continue. You can always pause it, right? Here we go, 5. Janine decides to take a ride on the Ferris wheel. Sorry. Partway up, she realizes that she remembers Mr. Erickson talking about sinusoidal equations in grade 12 math. Sure you do. She determines that the equation that models her height above the ground as a function of time is given by the equation below, where h is the height in meters, t is time in seconds. So we've got time and height being compared. And there is the equation. Okay, we have that. What is the period of this function? Explain the meaning of the period in this context. We've done a lot of this, but the period is 2 pi divided by b, which is 2 pi divided by 0.0698. That is b right there. And let's figure out what that is. I'm doing this live as I'm creating the key. So that's 90.017 if it rounds, and that is in seconds. Okay, in this context, period is the time it takes to go from a low up and then back low, right? That distance is approximately 90 seconds. The meaning is, right, it takes approximately 90 seconds to go from the lowest point of the wheel to the highest and back to the lowest. Okay. B. For how long out of each rotation around the wheel is a passenger more than 60 feet above the ground? Show your work. Okay, so we're gonna y2 is equal to 60, second trace 5. We're gonna find that intersection, but first I need to enter that equation. There we go. Let me see here real quick. I'm just going to go 40 plus 40, approximately that'd be 80 on the high end and almost zero, like 0 on the low end for the y's, right? I'm going to go minus 1, but y max will be about 80. Just so you make sure you understand that. And the max is appeared as 90 seconds. I'm going to go 120, something like that, and there you go. Should probably go a little bit higher with the y max. Oops, too high. 100. There we go. There I have everything. So y2 is equal to 60. I think I will have to change my window. Not really. So I'm just going to focus on these 2 points, subtract, and that will be it, right? Alternatively, you could find these 2 points, subtract them, but then you will find the time below within a period, right? So you need to take that number away from a full period to figure out these little chunks here. I'm going to go the shorter way, okay? So let's find that one. And remember 4 decimals, 81.9728. That is x2 is 113.0696, right? So the delta time will be 113.0 so forth minus 81.9 and so forth, and delta time will be that's 31.10 seconds. There we go. Done. Next. How many are left? I just want to check if I have enough time. I think I might have enough time to finish this, okay, before my class. Students studying a pendulum in physics class notes that the horizontal position of a pendulum from a sensor varies sinusoidally. She notes that the minimum distance that the pendulum reaches to the is 5 centimeters from the sensor. I think that was just a typo. 5 centimeters from the sensor is the minimum distance. And a maximum distance from the sensor is 27. She finds that for the pendulum to swing from one side to the other, it takes 1.2 seconds. So let's take our time here. I'm going to highlight the fact that the pendulum is swinging. It gets as close as 5 centimeters and as far as 27 centimeters from that sensor, right? And that it takes from one side to the other, it takes 1.2 seconds. I don't know if you noticed that, but it doesn't say a full rotation here, right? It just says from one side to the other as it's swinging is 1.2. So that's half a period, right? Half a period. I'll just do that. Exclamation mark, right? Half a period. So a timer is started when the pendulum is closest to the sensor. So you're at a min, right? Create a graph of the position of the pendulum for the first 3 seconds. Label your graph. Just so you know, this is walking you through the X scale, Y scale starting point. That's what this is doing. I'm going to continue with my method here. So this is our Y scale. Y scale. Okay. X scale. How would we do that? The period is 2 times 1.2, which is 2.4 seconds. Because if this is the pendulum that's swinging, right, and this is the sensor, we know that at one point we are 5 centimeters away, and when it swings over to the other side, right, from here to there, it's 27 centimeters. Okay, so you just have to make sure you understand the distance is horizontal here, but really for us, the distance will be our y and time will be our x variable. So you kind of just have to be okay with that. But the lowest, the y min is essentially 5 centimeters, and the y max is essentially 27 centimeters, right? We don't have the amplitude in this case. And that's fine, right? So I'm going to highlight these green because I did that up there. These are given. You can now find the mid, right? 27 plus 5 divided by 2. That's 32 divided by 2, which is 16 centimeters. And let's check. It's 11 from here to here, 11 from there to there. It kind of makes sense, right? So your Y scale is technically taken care of. Your X scale, we're still not quite done. We need to go 2.4 divided by 4, which is 0.6 seconds. So those are the increments, right? Okay, so I got the X scale, I got the Y scale, right? I've got that figured out. Now I need to have a starting point. A timer is started when the pendulum is closest to the sensor. The timer is started, right? Let's see here what other colors I have. Timer is started when the pendulum is closest to the sensor. That's a starting point, right? So I'm going to say basically that is telling you you're going to start here. Okay. And specifically at a time of 0 and at a height of 5. And so you know you're going up and back down. And it takes 2.4 seconds to get back to 5. You know this is 2.4 because you start at 0. If this had been something other than 0, you have to add 2.4 to get this, right? And we go up by 0.6, 0.6, 16, 1.2, 27, 1.8, 16, and 22.45, right? So we've got our 5 points there. It says to graph it. B is determine the equation. I'm going to kind of go against the current here and just go with the equation. So stat calc 5 sorry, not 5, sin reg. Gotta be careful. And so just enter that. 0. There we go. 11 sine 2.6180 x minus 1.57 plus 16. It jives. There we go. That's our equation. And then we want to graph it. I'm going to graph it just now. Here's the graph. Kind of going against the current there, right? But that's okay. I never go into the negatives. It says for 3 seconds, right? So this is technically 2.4 seconds. So I'm not sure why that asked us. I just got this question from someone. Okay. So this is time in seconds, height, and not height, sorry, distance. I like this question because it makes you think, right? We're not doing the same thing as before. Centimeters. This is distance from sensor to be specific, right? And I'm going to go 0.6, 1.2. I'm going to go up by 0.6 because we start at 0. Why not? So 1.2, 2.4, 0.6, 1.8, 2.4, right? And then it's just 3.6 and so forth. So I'm basically going up by 0.6, right? Oh, this is exactly 3.0, right? So that's just the choice that and this is going to go to 30. 10, 20, 30, yeah, that's going to work. 10, 20, 30. And so my lowest is at 5, just right about there. The highest is at 27. The mid is at 16. There you have it. So at 0, I'm at 5. It's actually my y-intercept. At 0.6, I'm 16. 1.2, 27. 1.8, I'm back to the middle. 2.4, I'm here. 3, be right there. So remember, you're going like this. Should never surpass your min or your max. Okay, there we go. There's your graph. C, what's C asking? Pendulum loses momentum, it travels less distance to each side of its resting point. However, the length of time required to travel from one end of the swing to the other remains the same. Explain how this would change the equation that models the position of the pendulum. Well, that means that the period stays the same, so it wouldn't change B. I would say you change, because this is half, this is the midpoint, that would stay the same, so you would change A, right? For C, decrease the amplitude only, right? Example, y is 5 sine 2.618x minus 1.57 plus 16. Okay. Because the idea is that the resting point of 16, right? 16 is like your mid here. That would stay the same. It's just that now it's swinging less back and forth. So the max and the min is affected only, right, by that. So here we go. Hope that made sense. Oof, I'm not going to have time to do this one on the video unless, let's see, determine the equation that models. So the decay, we are talking decay, and determine the equation that best models this. Probably going to be an exponential. So 0, 1, 1.75, 100. Oh, you know it's exponential. How do I know that? Because it has a y-intercept. You can't have a y-intercept with a logarithmic. Okay. I'm just going to view the plot real quick. I'm going to have to stop this here. Yeah, but because of that, it's exponential. It's decreasing, which means that the value b is going to be less than, between 0 and 1, right? So I'm just going to maybe press record one more time when it's all worked out.